All right, so section 19 is kind of broken up into two different things. So we're reviewing inverses and we're reviewing exponential and log equations, which you'll feel very good about those. You'll be like, oh, I remember all this. And then we're also learning how to take the derivative of an inverse, which is kind of strange. Okay, so we're going to start out with the kind of strange thing and we'll do the easy stuff. All right, so kind of reviewing, a function is called one-to-one if it never takes the same value twice. So if you have f of x1 is not equal to f of x2, whenever x1 is not equal to x2. So what that's saying is you could never have the same y values if you have different x values. Okay, basically it passes the horizontal line test. So things like x squared, like if you have y equals x squared, it does not pass the horizontal line test. Okay, because if I draw a horizontal line through, maybe I have the point 2, 4, but I have a different x value, -2, that has the same y value. Okay, that's what I'm saying there. Okay, does that make sense? So this does not, we say, does not have a unique inverse. So no unique inverse, because it fails the horizontal line test. Okay, so a vertical line test would see if something's a function. This sees if it has an inverse. All right, and then f of x equals, or g of x equals x cubed, right? It's a function that looks like this. This one actually passes the horizontal line test. So as I draw a horizontal lines through, it's never crossing at more than 1 point. Okay, so passes the horizontal line test. So that means it has a unique inverse. Okay, so who can remember from Algebra 2 how you find an inverse? What do you do? No one. Yeah, Spencer. Yeah, you just switch your x and y, and then you solve for the new y, right? So if I'm finding the inverse for this, I would do x equals y cubed. And then I'd solve for the new y. So I'd have y equals the cube root of x. That would be what we call g inverse of x. Okay? And it ends up being a reflection over the line y equals x. All right, but if I tried to switch this one, if I did x equals y squared and I took the square root, what do I have to write when I take the square root? Plus or minus, okay? That's actually two functions. It's not one function. That's why it's not a unique inverse. So two functions. Okay. So for number 2, it says find the inverse of f of x equals x cubed plus 2. So this is pretty straightforward. We switch our x and y's. We solve for the new y. So when I do that, I have x minus 2 equals y cubed. I take the cube root of both sides. I don't need a plus or minus because it's the cube root. So I have y is equal to the cube root of x minus 2. So instead of writing y, what I'm going to write is f inverse of x. Okay, so if I sketch this out, we know what y equals x cubed plus 2 looks like. It looks like x cubed, except it's been shifted up 2. So the original f of x looks like this. And then the inverse is going to look like the cube root function, which the cube root function looks like this, only it's been shifted to the right 2. So we're going to start at 2, 0, and it's going to look like this. Okay, and if you notice that these two graphs are symmetric, if you fold across this line right here, the line y equals x, every point that you had, like this point we had 0, 2, and this point is 2, 0. So every point on the graph is going to be the opposite x and y value. So if I have the point 1, 3, then I'm going to have 3, 1 on the other one. Okay, so number 3, it says find the inverse of this quotient. These ones are a little bit harder. So we get x equals 4y minus 1 all over 2y plus 3. And we need to solve for y. So luckily we've done that entire section on implicit differentiation because we had to use this skill a lot when solving for dy over dx. So basically we want to get all of the y's on one side. So the first thing I'm going to do is I'm going to multiply the denominator over. So I get 2 times xy plus 3x equals 4y minus 1. And I'm going to get all of the y's on one side. Okay, so I usually try to get it on the side that's going to make the least number of negatives total. So I would probably, I don't know, add the 1 over to the left and subtract the 2xy over. So 4y minus 2xy. Now I can pull out the y. You could actually pull out 2y, but we only want to pull out y because that's what we're trying to solve for. So I get 4 minus 2x times y. So when I divide by the 4 minus 2x, I have 3x plus 1 all over 4 minus 2x equals the y. So equals g inverse of x. Okay, so even if they're more complicated like that, we can still solve for it. Okay. So part A, I shouldn't say find the inverse of the function. If I did try to find the inverse of the function, I'd have x equals y cubed minus 4y. And then how do you get the y by itself? You can't really pull out the y because you still have a y squared. So I'm not going to have you guys find the inverse. Okay, but I am going to have you find the derivative of f of x and its inverse. So let's start with f of x, and then we'll talk about f inverse of x. Okay, f of x is really easy. F of x is equal to x cubed minus 4x. So if I'm finding the derivative of f, I just get 3x squared minus 4. Done. I should give myself more room here for the other one. All right, but what if I have f inverse of x? Well, we don't know how to actually solve for f inverse. You can. There are ways to do it. We're not going to talk about that, though. We're going to use implicit differentiation. So we're going to start with x equals y cubed minus 4y, which we know is an equation for the inverse. We switch the x's and y's. And we're going to do our implicit differentiation. Okay, so I'm going to divide, or I'm going to take the derivative of x. So I get 1. The derivative of y cubed is going to be the 3y squared, but since it's a y term, we tack on the dy over dx. And we have minus 4 dy over dx. So we get dy over dx. We pull it to the front. So we have 3y squared minus 4. So dy over dx equals 1 over 3y squared minus 4. So it's kind of weird notation because we're talking about dy over dx, which makes you think of y prime or f prime of x. It's not really f prime, it's f inverse prime. So really, the way we write this is f inverse prime of x. There's a lot going on there, isn't there? So you can write dy over dx just as long as you know that it's for the inverse, right? Okay. So it says in the original function, we had the point 2 comma 0, right? So in the original function, we had f of x equals x cubed minus 4x. If we plug in 2, we get 2 comma 0. Okay. So that means on the inverse, we're not going to have 2 comma 0. We're going to have what point? 0 comma 2. We're going to have it flipped, right? The x's and y's are going to be flipped. So we're going to talk about the derivative at each of these points. So in our original function, right, we had f prime of x equals 3x squared minus 4. So if I'm finding the derivative at 2, I get 3 times 2 squared minus 4. So 12 minus 4. So I get 8. So let's talk about the inverse. So our inverse was dy over dx equals 1 over 3y squared minus 4. Right, so you can go back and check. Right, that was it. And this is for the inverse. So if I'm finding its slope at the point 0 comma 2, the y value is 2. So we get 1 over 12 minus 4, which is 8. Okay, so we have 8 and 1/8. What do we notice about those? Reciprocals, right? Not quite opposite reciprocals. They're not perpendicular to each other, but they are reciprocals. Let's see if that always happens. So part E says find the slope of f of x at the point -3 comma -15 and compare it to the slope. I don't know why my little inverses didn't print, but it should be f inverse of x at -15 comma -3. So the slope for f of x is going to be f prime of x equals, it was a 3x squared minus 4. So we're going to have 3 times -3 squared minus 4. So we get 3 times 9 is 27 minus 4, so we get 23. All right, so now if I take the inverse, its slope is 1 over 3y squared minus 4. So it's 1 over 3 times negative 3 squared minus 4. Notice how like the y that we're plugging in was the x from before. That makes sense, right? So what are we getting? 1 over 23. So it always happens. Okay, so what we're saying, so maybe if I go back to the picture where you could see the symmetry, what we're saying is that if we find the slope at, let's say this point, 1, 3, the slope right here, it's similar to the slope here. Okay, but they're not exactly the same. You can tell that they're not parallel. Same with the 0, 2, this slope and this slope. They're not parallel. They are both positive. Okay, but one's really steep and one's not so steep. Okay, and you can see even with some other, like here and here. Okay, they end up being reciprocals of each other. So if one of them was 2/3, the other one's going to be 3 over 2. Not opposite reciprocals. A lot of people get that wrong. Okay, and why is this true? It's true because if you think about how to find the slope in Algebra 1, like what's the slope formula that you guys use in Algebra 1? How do you find the slope between 2 points? Yeah, change in y over change in x, right? So to find the slope between 2 points, you always did y2 minus y1 over x2 minus x1. So that was for some function where you had 2 points, x1, y1, and x2, y2. But on its inverse, oh, I should have drawn this better. There's no way I can draw that. Okay, but it's on its inverse, we have the 2 points, y1, x1, and y2, x2, right? We switch our x's and y's. So when we find the slope for the inverse, it's just x2 minus x1 over y2 minus y1. Okay, and since derivatives are really just finding the slope, right, even though we use limits to find it, it's the same thing. That's why it ends up being reciprocal. Does that make sense to everybody? Okay, so that's a weird theorem that you have. This theorem doesn't show up all the time on the AP test, but it could definitely be like the difference between getting a 5 on the test and a 4 on the test. Okay, it shows up occasionally. Maybe there will be 2 questions that involve this, but these are 2 questions that you're getting right just because you filled out a note card and you memorized this formula. Okay, so here's the formula. It says if you want to take the derivative of an inverse function at a certain x value, what you can do instead is you can do 1 over f prime of f inverse of a. Okay, so it seems a little bit weird. What I always tell people is that if you do inverse and then you do prime, you're going to do 1 over and then you do prime and then inverse. Does that make sense? So you switch these two inverse and primes. Prime and then inverse. Does that make sense? Okay, so that's the easiest way to memorize it. All right, so number 1. So it says use the formula to find f inverse prime of a. So number 1 is a classic example of why you would need this formula. Okay, because you can't find the inverse. Okay, if you try to find the inverse, you have x equals 2y cubed plus 3y squared plus 7y plus 4. Huh. Can you solve for y? No. Like, how do you solve for y there, right? So you can't find the inverse. So if you can't find the inverse, how do you find the derivative of the inverse, right? We don't know how to find it. So what we do instead is instead of doing f inverse prime of 4, we end up doing 1 over f prime of f inverse of 4. And when it does show up on the AP test, it's always super simple to find the inverse part, this f inverse of 4. Okay, what we're saying is, on our original function for f of x, we can plug in something and get 4 out. Okay? Because we want to have, for the f function, we want to be able to plug in a number and get 4 out. So on the inverse, we want to be able to plug in 4 and get that number out. Does that make sense? Okay, so what number? You can always do it very quickly in your head. what number in the original can I plug in to get 4 out? 0. Do you guys all see that? It's always something super simple. It's like 0, 1, somewhere around there. All right, so it's 0. All right, we're saying, when is f of x equal to 4? So when is 2x cubed plus 3x squared plus 7x plus 4 equal to 4? At x equals 0. And there's only one, because it has a unique inverse. There's only one place. All right, so that means on the inverse function, when we plug in 4 for x, we get a y value of 0. That's what this is saying, f inverse of 4. It's saying when I plug in 4 for the inverse function, what do I get out? I get 0, okay? So we have 1 over f prime of 0. Can you find f prime of 0? Sure. F of x was 2x cubed plus 3x squared plus 7x plus 4. So f prime of x is 6x squared plus 6x plus 7. So f prime of 0 is 7. So this answer is 1 over 7. That's it. So even without finding the inverse, we can get the solution to that. Does that make sense? All right, so the next one. So now we have f of x equals 1 over x minus 1. Can we find the inverse for this one? If I switch my x and y? Yeah, you can actually find the inverse. It's not that bad. You have x times y minus 1 equals 1. Xy minus x equals 1. So if you're solving for the, well, I should have made that easier. That's fine. If I'm solving for the y, I'm going to add the x over and then divide by x. So that's the inverse. So can I take the derivative of that? Yeah, you can actually really easily take the derivative if you bring the x into both pieces. So the derivative ends up being negative 1 x to the negative 2 plus 0. So if I'm asking for f inverse prime of 2, right, that was f inverse. So f inverse prime was negative 1 over x squared. So we get negative 1 over 4. So that's one where you don't necessarily need the formula because you could find the inverse. Okay, but if you can't find the inverse, you need that formula. Does that make sense? Does it work the same way without it? Sure. The other way would be to say, okay, I want f inverse prime of 2. So I want 1 over f prime of f inverse of 2. So you're saying, what x value do I plug in to get 2 out as my y value? So that's where it gets a little bit tricky because you have to solve 1 over x minus 1 equals 2. So you get 1 equals 2x minus 2. So 3 equals 2x. So you get x equals 3 over 2. So what that's saying is for your f function, if you plug in 3 over 2, you get 2. So for the inverse function, if you plug in 2, you get 3 over 2. So f inverse of 2 ends up being 3 over 2. So you have f prime of 3 over 2. So if you find f prime using either the chain rule or the quotient rule or whatever, you will see that it ends up, f prime of 3 over 2 ends up being negative 4. So you do get negative 1/4. So you can go through all of the work, you still get the same answer. So either way on that one. All right, so this one is one where you can't find the inverse. So it says, what is the value of f inverse of x when x equals 3? So what we're asking there is f inverse of x equals, oh wait, f inverse of 3 is equal to something. In other words, we're saying f of that something is equal to 3. It's usually something very simple on the AP test. So even if you didn't have a calculator, you should be able to figure this out. So what we're saying is 1/4 x cubed plus x minus 4 equals 0. Okay, the first thing I always try is 0. I'm like, okay, please tell me 0 works. If you plug in 0, do you get a true statement? No, you get negative 4 equals 0. It doesn't work. If you plug in 1, do you see how you'll have a 1/4 that you're not going to get rid of? You're going to have like a fraction for the answer. So it's not 1. What's a good number to plug in so that when I do x cubed and I divide by 4, I get like a nice integer. 2. Okay, let's try 2. So I plug in 2. I have 1/4 times 2 cubed plus 2 minus 4. Is that equal to 0? 8 times 1/4 is 2. 2 plus 2 minus 4. Yeah, it equals 0. So 2 is what we're looking for. So f of 2 is what gives us 3. So that means f inverse of 3 gives us 2. That's what we wanted. So we did the first part. So then it says, well, what's the value of f inverse prime of 3? So it's 1 over f prime of f inverse of 3. So luckily we've already found that f inverse of 3. So it's 2. So we 1 over f prime of 2, so we just go back to f of x equals 1/4 x cubed plus x minus 1, and we take the derivative. So we get 3/4 x squared plus 1, and we plug in 2. So we have 3/4 times 2 squared plus 1, so I get 3 plus 1, which is 4. So our answer is 1 over 4. Okay, do you guys understand how that works? So occasionally that will pop up on the AP exam, not often, but I've seen it on some of the more recent exams. Okay. All right, so let's kind of do the review part. That's the part that you guys like. So do you guys know all of these formulas? A to the x equals y, if log base a of x equals y, right? Log of a times b equals log of a plus log of b. Log of a over b equals log of a minus log of b. You've all seen these in Algebra 2 and Pre-Calc. You're pros, right? You remember all these formulas? You can pull powers to the front, right? If you have things like log base 3 of 3 to the 7, you should know right away that it's just 7. Or if you have log base, or no, wait, let's do 8 to the log base 8 of 9 is just 9. Those are the inverse properties. Change a base. Usually with calculus, you want to change to natural log, not log base 10. And you can even do limits. We know that a logarithm always looks like this. It has a vertical asymptote. It does not have a horizontal asymptote. So as you go to infinity, it actually does go to infinity. It just goes very, very slowly. For instance, if I did log base 10 of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 of this lovely number, what is that? Million, billion, trillion, 1 trillion? What would our answer be? 3, 6, 9, 12, right? So you have 12, like 10 to the 12 is what gives you that, right? So it goes very, very slowly. That's only at 12. So it's going to go to infinity. It's just going to go very, very slowly. And then the limit as x goes to 0 from the right is going to be negative infinity. So as you get closer to 0, so you're tracing along the curve in this direction, you are going down to negative. Does that make sense? All right, do you know all of those properties? If you don't, I would learn them. All right, so you should be able to do these pretty quickly. So if you see log base 3 of 3, what you're saying is 3 to what power gives you a 3? Do you guys know this? 1. What's the next one? 8. It's the cancellation thing. 9 to what power gives you 81? 2. Ooh, how about the next one? 9 to what power gives you square root of 3? 1/4. Right. So if you didn't know that, you could set it equal to x. And you could write 9 to the x equals square root of 3. And then you could say, okay, well, 9, that's 3 squared. Right? You could try to get them to have the same base. So 3 squared raised to the x equals 3 to the 1/2. So 2x equals 1/2. You set your powers equal to each other, multiplying those powers. So you get x equals 1/4. So you could do it that way if you get stuck. Or you could just keep thinking, okay, 9. If I did 9 to the 1/2, I get 3. So I need to take the 1/2 power again to get the square root. So 3. All right. So this next one, I have subtraction. So how do I combine them? I divide. So I do 192 divided by 3. Anybody know what that is? Yep, it's 64. So what's log base 4 of 64? 3. Yeah, no one knows that one. It's one of my favorites. All right. So next one, I have subtraction and addition. So if I'm combining, I'm going to have log base 2 of 6 over 15 for the first two. But then I'm adding log base 2 of 20, so I'm going to say times 20. So I'm just going to put it on the top with the 6. So it ends up being log base 2 of 180 over 15, which is log base 2 of 8, which is 3. Okay, so some of them you can go all the way down to a nice integer at the end. All right, how about this next one? 1/2 of log of 16. So I know I can bring the 1/2 up as a power, but it doesn't really do me much good. I have log of 16 to the 1/2, which is log of 4. So on the AP test, you can actually leave your answer as log of 4. That is an exact answer. Okay, or you can round to decimal. Yeah?
20 times 6 equals
120. Oh, but I did get the 8 right? Yeah, I just memorized where I was going with that. All right, so 120 over 15, thanks. All right, so log of 4, you can't go down any further because it's base 10. So it's saying like 10 to some power gives you 4. Okay, so we don't know what that is. So if you wanted to round to 3 decimal places, you could on the AP test. You could leave it as log of 4, or you could round to 3 decimals. So if you do log of 4 on your calculator, you get 0.602. All right, the next one, is this a nice number? Yep, 2. And the last one, not a nice number. 2 to what power gives you 30? I don't know. A lot of people say 15. It's not 15. That's really big, way bigger than 30. 2 to the 15, right? But we know that 2 to the 5 is 32, so it's going to be a little bit less than 5. So what I would do here is the change of base. So we have log of 30 over log of 2, or you could do natural log of 30 over natural log of 2. So you can put it into your calculator. So we get 4.907. Is that what someone said? Yeah, that's good. All right. Okay, so an important concept in calculus is going to be expanding logarithms. Okay, the reason is because, do you guys remember chain rule? You always have to take the derivative of the inside. You're going to learn a formula for finding the log of x, like taking the derivative of log of x. Okay, but you're not going to have a formula for, like, b, finding the derivative of that. And can you imagine the chain rule? Taking the derivative of the inside? Yeah. Ugh, terrible. Look at that. Would you want to take the derivative? Ignore the log. Would you want to take the derivative of that? No. Heck no. We don't want to take the derivative of that. That's awful. So expanding logarithms actually helps us out a lot in calculus. So this is a very important concept. We should do more of this in Algebra 2 and Pre-Calc. So expanding the logarithm. So if I have log base 8 of 5y squared, I can break it into log base 8 of 5 plus log base 8 of y squared. And then I'm going to bring any powers that I have to the front. So really expanded, this is going to be, whoops, not 5. It's going to be log base 8 of 5 plus 2 times log base 8 of y. So then if I tried to take the derivative, it would be a little bit easier. What's the derivative of log base 8 of 5? 0. I heard someone say it. Why is it 0? Because it's a number, right? The derivative number is always 0. Okay, but then you would just still have to take the derivative of the other part, but it wouldn't be as hard as if you had the chain rule in that first part. All right, so this next one, so we expand it. So we break it into log of x squared. I don't know why I did big parentheses there. Log of x squared plus log of the cube root of x minus 1 minus, because it's on the bottom, log of 2x minus 1. And we know that powers go to the front. So I'm going to have 2 times log of x plus, what about this next power? What's the power? 1/3. So I'm going to have 1/3 log of x minus 1. Then I have minus log of 2x minus 1. That one can't break up any further. So that's it. And then likewise, because you have multiple choice on your AP test, you're going to have to combine things as well. Okay, sometimes your answer's in a different form. So knowing how to combine logarithms is important as well. So for this, we're going to go in the opposite order. We're going to bring the powers up. So we're going to have natural log of 6 plus natural log of x cubed plus natural log of x squared minus 2 squared. So we're going to have natural log of 6x cubed times x squared minus 2 squared. So it's the natural log of all of that. Gross, huh? All right, and the next one, so I'm going to bring the 1/2 up as a power. So I'm going to have log base 3 of y plus log base 3 of 81 to the 1/2. I'm going to bring the 2 up as a power as well. So plus log base 3 of x minus 2 squared. What about log base 3 of 81 to the 1/2? It's really log base 3 of 9, right? Which is 2. So we're going to write 2 out front plus, and we're going to combine this logarithm and this logarithm. So we're going to have plus log base 3 of y times x minus 2 squared. And that would be combining all of it. Okay, and the last thing we're going to have on our homework is solving logarithmic and exponential equations. So I'll do a little bit of that tomorrow. So we'll hold off on that for now. And I'll wait until tomorrow to do that because we're going to kind of running out of time. All right.